So yeah, good morning, everyone, and welcome. So we have the third lecture on short-range structure this morning from Dien, and then we have a break, and then another lecture after that, as we had it yesterday. So the floor is yours, and as I remember, you wanted to be interrupted if there are questions, right?
Sure,
so please use the raise hand feature in Zoom, and then we can schedule that and call it out. Yeah, and don't hesitate to ask questions.
Yes, add anything, and I try to answer if I can, and if not, I will owe you some questions and get back to you later. Okay.
All right, good. So the floor is yours.
Yeah. Okay. So we can continue with the lecture today. So I hope you guys have a lot of fun with the machine learning session yesterday afternoon. So I would like to remind a little bit about what we have learned in yesterday morning session. I hope you didn't forget all about it. So yesterday morning session, we have learned a lot about the short range correlation SRC. So I just want to have a quick summary what we have learned about this object. So we know that SRC is responsible for high momentum tail, and they account for around 20% of the nucleon inside nuclei. They are the pair with back-to-back with a small central mass momentum. And the special feature, and it is so important, we will do it today as well, is the NP dominant over NP is dominant in the SRC by factor of 20. And this is the universal behavior across the different nuclei. And we also have some time to discuss about SRC in neutron-rich nuclei. And we learned some interesting feature as well, is that in the neutron-rich nuclei, the proton, they have a high momentum fraction, or in the simple way, the proton will speed up in the neutron-rich nuclei. And that one, with that, we kind of have a understanding that when we're adding more neutron to the system, this neutron will correlate with the core proton. So that is why it brings more proton from the mean field to the SRC region. And we still have a lot of things to learn about SRC. We have many near future experiment in order to study different aspects of SRC as well. And in terms of the neutron-rich nuclei in SRC, it has a very important application to the neutron star. And for today's lecture, we can continue study about SRC. I would like to discuss with you two more topics. Is study like nucleon-nucleon interaction. That is one of the avenue help us to learn more about the SRC. And then one more like implication of SRC connected to the EMC effect. We will talk about it in the next lecture. And in the end, I promise we will watch the Proton movie together. So let's try to get there so we have a time to watch the movie together. So like when I discussed about why SRC is very important, I already mentioned that we need to study this SRC across different scale. It means that in the many body system, and then we need to, that is what we have been discussed yesterday. So today we will go to one more deeper level, is an NN interaction. So why we care about this NN interaction. So as you see that when we have like any the model, right? So this NN interaction, it is the initial input for calculation. So I be initial the structure like reaction calculation, and it also will be the input for many other calculation from the dense system, the neutron star, or many other things. So this is a very crucial ingredient. So we need to understand how the NN interaction work in order to understand our nuclear structure. So that is why we need to study this object. So in fact, that there are many avenues you can get the NN interaction. So many people from the theory side do calculation or do the fitting, as it is the selection of the little NN interaction. So you can see that many of them there. So what is the current situation with the NN interaction? So I remind you a little bit. So we have a Hamiltonian, right? So we need this NN interaction to block in order to have a Hamiltonian. When we have a Hamiltonian, we will do a quantum, like numerically quantum Monte Carlo calculation in order to numerically solve the many body Schrodinger equation. According to limited power, it cannot do for everything, but we can do it for some of them. So it depends on the NN interaction model you put in to build that like Hamiltonian. You will able to get different way, like different set of parameter of the wave function. So after you have a wave function, you can use that to calculate the different quantity in order to understand structure function, understand structure of nuclear. So this is one of the example. What I'm showing here is the two-body density in the distance space R and in the momentum space D, momentum space Q. So when you take a look at the picture, they are using different NN interactions. I list 4 of them right here. So we take a look at this picture, we can see that all the calculations seem pretty reasonably agree with each other at the low momentum or at kind of like at the far distance. So reasonably well agree with each other. But now when we take a look at each of the high momentum, so you can see that it is really diverse, very big difference. Or at this is a short distance and this is at high momentum. And we have been discussed about that so far. So this is the area where the SRC is dominant. So we need to put all this NN interaction in to test it, to see like, oh, we have so many. So which one works the best? And or at least we should know this NN interaction work with in what region of kinetic setting. So we can rely on calculation and understand what we are doing. So this is the current situation. And then how we going to test this NN interaction? So the way to do it, it like follow very much like feedback chart I talked to you from very beginning. So we will measure the nucleon knockout cross section. We will knockout cross section. And then we will compare with calculation using the different NN interaction and the modeling of the different type of reaction. And then we will see which one works the best. So then we can benchmarking our understanding of the NN interaction. Like we know where we are. So the situation is that for the calculation, we taking the data in the wide range of nuclei from light to heavy. And we also have some effective theory in order to do some calculation for different type of nuclei, not all of them, but many of them. But in terms of the precise calculation, we only have a precise calculation for light nuclei because it's so complicated system, right? Like I mentioned as well, it's about challenging of the many body system. So only with the light nuclei, we will have a precise calculation. So that is where we want to test our theory calculation. Because if we have data, we have precise calculation. So that is the perfect place to do the benchmarking of the calculation. And that is why we want to use the A=3 nuclei to do this study of NN interaction. So there are one system, it's very unique and we call it like mirror nuclei. So that is helium-3 and tritium together. Both of them have 3 nucleon inside. And we call it the mirror nuclei because of like, you can see that the proton, it have a helium-3 have a 2 proton, 1 neutron, and opposite, tritium have a 2 neutron, 1 proton. So we think about it like image through the mirror together. So by doing the measurement on the both of them, we were able to constrain the reaction mechanism. And one of the other reasons is that measuring the proton in the experimental is way easier compared to measure the neutron. So we can measure the proton inside tritium, and it should kind of like similar, give us the similar information like the information of neutron inside helium-3. So that is advantage of this mirror system. And because it is A=3 system, we have exactly calculable and it has precise calculation. So this is the perfect, the ideal place in order to test and benchmarking theory. So that is the reason we go to A equal to 3. Another thing I would like to remind you is we are using the quasi-elastic scattering, like we discussed a lot about it yesterday. And we using the blend wave impulse approximation, PIWA. Yeah. So in this approximation, you remember that we assume that this virtual photon, it only interacts with a single nucleon inside nuclei. And when it gets knocked out, it don't have a rescattering with the residual system. And within this approximation, we can calculate the missing momentum, either missing momentum from the Q vector and the final vector. And this missing momentum will very well approximately equal to initial momentum of the nucleon in the knockout reaction. We need the initial momentum of the nucleon in order to understand about the motion of the nucleon inside nuclei. So it works within the plane wave approximation. And within the approximation, the cross-section can be factorized by kinematic factor K, and elementary the cross-section of electron on the proton and the spectral function. The spectral function is the probability of finding a nucleon inside nuclei with a given energy EI and momentum PI. So that is like, we keep this picture in mind. And now we will see how we can study it. We take the data. We have data on Z A equal to 3 system before. So I think this is the data from the whole, let me see, Z whole A of the J Lab in 2005. Well, it almost 20 years ago. It's older than I thought. So they measure the cross-section and then on helium-3. And then they do some the transform and calculation in what they call effective density. So then you can see the data point. Can you see my cursor moving? I hope yes. Okay. Yeah. So this is the data. We measure is it data, and this is the prediction from the plane wave approximation. So what you are seeing here is that the data, there are big difference, a lot different between the data and the plane wave approximation. And I mentioned that if we want to study about nucleon distribution, like the initial information of it, it should follow the plane wave approximation, right? But now with this big difference, it means that we kind of far off from that picture, from that like approximation. So it means that this data, it can be very useful to study the reaction mechanism, but it's so far off from like that original, the initial information of nucleon. So it's not that useful to study about the nucleon distribution. And now you may question, why is that? What makes the data so far off from the plane wave approximation? So the reason is this: in experimental data, we always have an issue, have a challenge in order to separate what we measure, what we want to measure, and other background. And it's the same picture right here. So this is the plane wave approximation. Oh, there are someone have a question in the chat. Oh, thank you. Yeah. So this is the plane wave approximation, the diagram, like I mentioned. So this is what we want. But in the experiment, we have many other, like the reaction channel. It is not quasi-elastic, but the final state is the same. So final state here means that, oh, you have the proton not out there. So you will detect all of them, but all of it like non-quasi-elastic, it will contribute to that final, like almost look the same, but not what we want. So some of them is the mesonic chain, some of them are isobar configuration, and the other is the final state interaction. So let give you a little bit introduction about what are they. But so for example, the meson exchange here, so it means that it's a virtual photon. Actually, it interacts with the virtual meson in the being exchanged into interaction of the two nucleons. Or for example, on this one, the virtual photon, it come in and it excites a nucleon to the delta, the isobar configuration. And then this delta will interact with the nucleon through like delta nucleon to nucleon. So they are the same final interaction. And another one, it more difficult, is a final state particle. It means that after it interacts, it get knocked out and it rescattering with the remaining, the residual system. So all of this one, it come into the measurement. So if we want to really study about the initial information of nucleon, you need to find a way to minimize all of this non-quasi-elastic effect so that your data is getting closer to plane wave approximation picture. So that is where you have a more sensitivity to study about nucleon structure. So this one is a very good overview paper from the theory people. And in this one, they have a much more detailed discussion about all these processes. I just have a very quick introduction to you. And they do calculation about what is the contribution of all of this like process of this mechanism. So based on their calculation, we will able to study that if we select a specific kinetic region, for example, where XB bigger than 1, then this iso configuration will be suppressed a lot. Or if we want to suppress this meson exchange, we need to go to Q square really high. So this contribution will be suppressed. So I highly recommend you to go to take a look at this review paper so you can have a better understanding about all this known quasi-elastic contribution and what the calculation they have been done in order to suppress this process. It's so much information there. We cannot go into detail. So I will only give you a big picture here. So detailed information, check this out. So that's about isobar configuration and the meson exchange. How about the final state interaction? So for final state interaction, we have a calculation from Misak Sassion from Florida. He very much like expert of the A=3 system in my point of view. So what he calculated here is the full process of E by P, and the y-axis here is you can think about it like a side of the final state interaction because it is from full divided by plane wave approximation. As a function of the angle between the recoil nucleon and the Q factor. So this one we can reconstruct it into experiment measurement. So from this calculation, you can see that so the final state interaction seem to have peaked right here. So it really big effect if this angle is around 70 something. But if the angle is smaller here or the larger here, this effect is much smaller. So in our measurement, we are going to use this information to select the data smaller than the 40 degree here. So by selecting this kind of specific kinetic region, we will able to put the constraint on the contribution of the non-quasi-elastic mechanism so that we can get closer to plane wave approximation picture so we can have a sensitivity to study about nucleon structure inside nuclei. So this is the data we took in the whole A on both helium-3 and tritium. So first step we did is that we get the absolute cross section, and then we compare this absolute cross section from the data with the different. All of them are like the most how I should use the word the most comprehensive calculation for A equal to three system exists so far. So we will have it from the CK-CC1 calculation. The another group is Krakow and the Misaksassian. So the idea is that these calculations, they all calculate. The first one is they all use plane wave approximation, but they will use a different like interaction, the NN interaction. They also adding in the different the final state interaction. So for example, there are two different type final state interaction they add in this calculation. So for this one, the interaction is between you knock out the proton, right? So then you will have an interaction between the two spectator nucleon, or you will have a final state interaction between the leading proton with this system, the radio system. So it's a calculation I listed here. They include different things. Yep. But one thing I would like to emphasize here is that the CK-CC1 is the one we are using like what we call factorize. I mentioned before. So it is an approximation. Like we use cross-section as the kinetic term, cross-section and the spectral function. So this is like factorize calculation. But the Krakow calculation here is more like a full calculation. So later on, we will see how well this calculation describe the data. Then we see that factorize assumption, how well it works compared to full calculation. So now in order to get it, like in order to see it clear, what we do is we will take the ratio. We will take the ratio of the cross-section experimental measurement to the plane wave calculation from that tree model I just present to you. Yeah, and then we will take a look at the ratio 44 tritium. So as you can see that if for the Krakow calculation, within the arrow bar, it describes the shape really well. So this black band here is around 10% and this like a little bit shallower is the 20%. So it looks like that this full calculation, it can describe the data within 20%. And then for the factorize calculation, it's a little bit worse. So it's about the 40%, the difference here. So one thing you can take away here is that both factorize calculation and full calculation could describe the shape of the data. But the full calculation do a better job. And you also can first time quantitatively see how well they agree with each other. So this is tritium. So now we take a look at helium-3. So the scale is changing a little bit. So similar, but quite different for helium-3 picture. So this is Krakow, full calculation, and the factorize again. So you can see that we don't have this good agreement over the range. So we can have about 20% agreement, maybe between from 100 to about 350 MeV. But on other range, it's getting bigger difference. You may question yourself now, why both of them are equal to 3 systems, but the calculation behavior like presenting the tritium better than helium-3? You can think about that now, and we may come back to that if you have answer later. So then we compare a little bit with the briefer data. So one I mentioned with you that it have a large difference between the plane wave and the data. So this is the briefer data. So we can see that now if we select that specific, the kinetic setting, we are under we control the much better. We have better control on the minimizing the non-quasi elastic contribution. So that is why we have a much smaller difference between plane wave and the data compared to before. So before you can have the factor 3, 4 or here, right? But now it's within 15%. That's not bad. So it means that this new data, we will have a much better sensitivity to what we want to study is the initial information of nucleon. So now we think about it. Oh, they are the neural system. Like they have a different configuration, the proton and neutron. So if it due to some of the isobar configuration there, if we add them up together, the effect will cancel. So that is what we did. So now we get the cross section, the total cross section of the helium-3 and tritium from the experimental, and now we divide for the calculation. And this calculation is showing here is from the mixation that it includes some final state interaction. So we see that, oh, so if we do this one, so crack out here and mixation here, so we see that if we have a total, this isobar sum, the data and the experimental, they agree pretty well together within kind of like 10% here, up to like 500 MeV. So that is really good. So you may think that, oh, 10%, what do you think? Why you think it's a big deal? But think back about it. How complicated this calculation is. And it like kind of like full calculation include different types of the reaction mechanism. And you can describe data up to the level of 10% within the error bar. That is very impressive result. So from this measurement, we are seeing that, oh, with NN interaction we use inside, and then we can see that data is well described within about 10% up to 500 MeV with our the most comprehensive calculation we have so far for A equal to 3 system. So this is very crucial benchmark for field theory nuclear calculation. And you know that we need to have this benchmark first because of like later on when we move to heavy nuclei, what we need to use is from this baseline, from the light nuclei, right? So we need to know that our first step is the benchmark before we can go to heavier nuclei. So that is what we have learned from A equal to 3 system. We also have this work have been published on in the 2020, and I put down this reference for you right here, so you can check out more detail about all these calculations we put in and how we compare between data and the calculation for this project. But this crucial benchmark is the thing I would like you to take it as a takeaway message from A equal to 3 system. So now we already have a study for light nuclei where we have a precise calculation with benchmark it. So we need to think about path forward to study heavier nuclei. So like I mentioned, right? So for precise calculation, we only can have it for the light nuclei here. So if we want to study about SRC in the heavier nuclei, we have data already. So next thing we need to have is the effective theory. So this is some theory can help us to study the SRC in the heavy nuclei. And the reason we need this effective theory to study SRC in heavy nuclei is that so it's very complicated and an interaction with the large nuclear density, right? So it's very complicated to describe it into true picture. So we only can go with effective way. And whatever we have the mean field theory, it doesn't include SRC. So we don't have available tool to study that. Give me a second. Okay. And AB initial calculation is only limited to nuclei. So that is why we need to go to SRC, effective theory. And that is where we enter something we call the generalized contact formalism. So this one we call it short is the GCF. So this is the effective theory for to study the SRC. So what is it like GCF? So as we studied so far, we know that we have a pretty reasonable scaling between the two regimes in the nuclei is the mean field regime, low momentum and high momentum is SRC. So they pretty well separated. So this contact formalism, the GCF1, it is effective theory. It relies heavily on this separation idea. So it means that in the nuclei, we can think about the interaction of these two nucleons at a really short distance. It's so strong, and it can decoupling with the interaction of the pair compared to residual of the rest of the nuclei. So based on this idea, if you accept it for a moment, we can do what we call a factorization of the nuclear wave function. Now you know that if we want to study these many objects, right? So we need many the body's wave function. So I think I have typo here. So we can write it many bodies wave function at the short like a product of two terms. So blue term here and A term here. So blue term here is a come from the two bodies wave function. And this one is the red term, it forms the A-2 residual system. So this is how we factorize the wave function in the GCF. So now we have a wave function. We can use it to calculate different physics quantity. So what we are calculating here is the two-body density in the coordinate system. So you can think about it as the probability of the finding two nucleons at relative distance r and central mass distance capital R here. So N here, it can be the different type of nucleon, and N, NP, and alpha here, it presents the spin of that pair. And A here is presented in the different nuclei. So we can write it in the term of C and the phi and N here, the blue term here. So this is the many body density, and this C term, we call it contact. So this is why we have the name of this model is the contact formalism there. And this is like two body density. And this one, it is universal. We can do this factorization in terms of the coordinate system, like R here. We also can do it in terms of the momentum. So the momentum here is the Q relative momentum, and the capital Q is the central mass momentum as well. So now, after we have that like two body density, we can do integration over R or over capital Q here. Then what we will get is the two body density as a function of relative R or the relative momentum Q here. So now how you do that? So for this function, this many body term here, we can use the quantum Monte Carlo to calculate it. So this, I don't know how to do that. It's a numerical method, and there are a huge group of people doing this one. So they can provide using the numerical method to get this two-body distribution. But the one thing we can do here is it is just like two-body, the two-body term. So this one, you can solve the Schrodinger equation for the two-body. So this is doable, and this is supposed to be universal. So from this calculation, from two-body density here, and if you have information of universal, you just need to solve it one. Then you will be able to calculate the Z contact formalism, this contact here for the different nuclei. And when you have it, you can use it to calculate different things. So that is the idea. So now we take a look a little bit at like how the two body momentum density look like. Why not go? Yep. So first we take a look at the calculation of the two body density using the AV18, the NN potential for different type of nuclei. So as you can see that here we are normalize all of them, like to have the same like the scale at like 1 Fermi, 1 Fermi like yeah 1 Fermi here. So the behavior you can see from this picture is that with a given NN interaction, what we are using here the AV18, you can see that at the short distance here, they have a universal behavior. So of course they have a very big difference in this large distance, but at short distance, look like for different nuclei, they follow the same pattern here. So that is where we can use it universal behavior in order to extract the contact term, the C here. So we can do calculation for using the different the NN potential. So as you can see that here I'm showing the different calculation corresponding to different NN potential. You can see that even though with the different NN potential, the behavior, the calculation give you the two body density are different, but the universal behavior are consistent between different calculations. For example, like AV18 here, AV4 here, or N2LO here. So you can see that at the short distance, they all collapsing and have a universal calculation. So the idea is that now we can do this calculation for different NN interaction, and then we can extract it, the contact term, by dividing that to the square root of this pair blue term right here. So you only need to solve this one. You calculated it for different type of pair. You calculated it using the different NN interaction, and then you can extract the C term here, the contact term here. So this is the in terms of the R coordinated system, and you can do exactly for the momentum coordinated system. So it's very similar picture. So for the momentum term here, so you also can have a two body density as the function of the relative momentum, and then you also have a two body term here in Q coordinated system. So then you also can calculate it here with the different NN interaction. And you can see that at the high momentum, they showing this scaling behavior as well. Then you will do the same thing, is using the two body density divide by square root of this one in the momentum space, and then you can extract the constant from this coordinated space. So after we have a Z contact term from both coordinated space and momentum space, we can use it to do many different things. Because now a lot of quantity, physics quantity, we can use the contact term in order to calculate it. And based on whatever we calculate, we can study different effects of the nuclei. So for example, here, I'm showing the contact term of the NP pair with the spin 1 ratio from different nuclei to deuterium. So this one is from helium-3, tritium, helium-3, and all of this one on the deuteron. And the square here is for R space, and the circle is for K space for different NN interaction. Do you notice one of the interesting feature here is that when you calculate it in R space or the K space for a given the NN interaction, they are consistent together all over the range of the different nuclei. And this one is similar, but it is for like PP, pair with the spin 0. So you may question yourself here, what does it tell? What does that mean? What it can tell you? So we say many times before that, oh, the SRC is responsible for the high momentum tail, and that is in the Q space system, in the Q coordinator. And we also said, oh, SRC is a pair with really short distance. And this one is one of quantitative things to show you that the short distance and the high momentum are equally together. Because this one is showing you that this constant, it is showing the behavior of the SRC pair, right? In the region, it's dominant. So either in the coordinator space R or in the K space, you can extract this constant, and they seem to be consistent together. So this is one of the way we can say that, oh, this short distance and the momentum are equivalent. So this work has been done by a group of very talented people who are working really hard on it. And the work has been published in the many different papers I listed here as well. So I think if you are interested in this topic, I highly recommend you to go and check out this paper here. So this is one of the things we can use the contact term from GCF in order to study the nuclear structure behavior. And now this contact also can be used to calculate the momentum, the one body density, the momentum distribution. We talked about it many times. So this is the equation to show you roughly how we can get the momentum distribution using the different contact term. Yep. And what we are comparing here is that we will use quantum Monte Carlo calculation there. That is what I mentioned with you, that it's very complicated and computational expensive in order to calculate. So the curve here is from the VMC. And the other one, we can just use the contact formalism. We calculated one and we can use it anytime now. So you can see that at the high momentum tail here, they are agree with each other very well. And this calculation this comparison also can repeat with many different nuclei. And you can see that using the contact term and using the VMC for different nuclei, they have a pretty good agreement. So this, I hope with it, I can convince you that the contact formalism is working well. So with this one, I think there are the message to take away from this lecture is that the A equal to 3 cross section is well described by the current theory calculation up to 500 MeV. So this is a very crucial benchmark in order to give us the confidence that our theory calculation is good for the light nuclei. So that is the first thing to take away. Second message to take away is that understanding this complex NN interaction is very challenging, but it's very important for nuclear physics. It's not just it is the tool in order to help us to understand the short-range correlation. And it also initial input for many other calculations as well. So see GCF, the next one to take away is that the GCF, we can extract that contact term from the GCF here, and that one it playing the role affected the theory for the SRC, and it working well, and it will allow us to study the NN interaction at the short distance and the high momentum for different type nuclei. So I can stop this lecture for here and take question if you have. Yeah. Today seems like everyone pretty quiet today.
That's right.
Hey, Dien, can you hear us?
Oh, yes, I hear you. Yes.
Okay, great. Yeah, we just used the microphone here in the room. Okay, yeah, so everybody's invited to ask questions, and we have some Actually, you're very good on time. So yeah, we have like 12 minutes left before the break. So please, everybody, go ahead and ask lots of questions.
I think there's a question from Erin. Go on.
Yes.
Yeah, so in the density function where you have the dip in Pn at like, I think 400 MeV, something like that. So I imagine this is coming from the tensor term, but is there anything, I guess, is there any more information you can give me as far as like where we think it comes from, or?
So this one is like, so this one is PP term and the Pn, the spin one term, right? So when we calculated the distribution, we see that this term is the tensor term, and it have kind of dominant here. So that is how it's behavior. I don't know how much more I can say about that. Yeah.
Okay, thanks.
Yeah. So
yeah. Do you know which is the model that is used in this calculation?
This one is used, I believe that this picture is AV18.
AV18, okay, thank you.
No, leave it open. So there's a question from Matteo also.
Hello, yes.
Yes.
Maybe I just didn't hear about that, but you speak a lot about the NP pair and PP pair, but you didn't speak about neutron-neutron pair.
Right. So I think like in the experimental, like what we really measure is that we can measure an PP pair, and we do like more like we can think about an pair as a in terms of like symmetry, and we believe that it behavior similar like PP pair, but we don't have a direct measurement in the n pair. Yes. So that's why I didn't talk much about that. But so I think that I have one question I dropped it during the lecture for you guys before, is that we see the agreement in better for tritium here, but when we go to helium-3, it looks like the agreement between calculation and the measurement is getting worse for helium-3. So did you guys have some thought about it? Why it make the difference between calculation and data in helium-3 is worse than tritium? Any thought about it?
So does that come back to the neutron-neutron interactions that you were just talking about?
You talk a little bit. You can tell me more detail about what you think, how that thing is affect this one. Why you think that one makes the difference in helium-3 bigger? Yeah. Is there any thought about it?
I mean, I have a feeling that, actually helium and tritium, the point being their mirror nuclei, but the issue is in where you have two protons, the Coulomb repulsion is much more higher as compared to just having two neutrons. So as such, the forces acting on both of these nuclei are very different. So
you're talking about Coulomb law, right? Between two protons. Yeah, that is one thing to take into that account. Yes, that is good catch. Yeah.
Yeah, but I don't know any other reason.
Actually, that is a good thought. Yeah. So we said that they are mirror nuclei, but you're exactly right. You kept a really good point. They are not perfectly mirror nuclei because it's Coulomb law. Because a proton follow that, but the neutron doesn't have that Coulomb law. That is one thing. But like, do you think about it? It is the nucleon-nucleon interaction. It's really strong compared to Coulomb 4, right? So of course that Coulomb 4, it makes slightly different between these two systems. But like it compared to that nucleon-nucleon interaction, it's so strong compared to that. So the contribution of the Coulomb 4 may be not that big to create this big difference. Is there something more as well? Think about the breakup reaction we are measuring is the EE by P, right? So we knock out in the one proton, form the helium-3 and tritium. what can happen in tritium in the final state, and what can happen in helium-3 in the final state.
So in the tritium, you'll never get the proton-proton pairs forming, of course.
Mm-hmm. How about in helium-3? So what is different?
So in helium-3, when you knock out a proton, you can get an NP pair left, but you can't get that in H3.
Right? Close enough. It's getting there. Yeah. So now we think about the tritium. We have a 2 neutron and 1 proton, right? So when you knock out the proton, so what is remaining is a 2 neutron, right? So we call it a breakup channel. It's a 3-body breakup channel. It means that you're breaking in the 1 proton and you will have a 2 neutron interact. So the final state is the proton, neutron, neutron. So for tritium, we only have 1 breakup channel. But for helium-3, it is much more complicated than that, like Erin and Alex just mentioned. So the first channel is that we can knock out the proton. And if the neutron and the proton, they stay intact together. So that one, you will have the final channel is the proton plus with a neutron. So that one, we will call that one is the 2-body breakup channel. But it also can follow other breakup channels that neutron not stay intact together. So it means that in the final state, you will have the proton, and the neutron. So that one you will have follows the 3-body breakup channel. So because it's helium-3, they have a much more complex the final state, how they break up to different channels. I think that's one of the reasons why it makes the calculation of helium-3 is more complicated compared to tritium. And that more difficult to calculate. It makes like more approximation most likely, and then it can kind of make the bigger difference compared to the data. So that is what we are thinking in terms of how to explain this big difference. But it can be more factors coming to this question as well. Yeah. So I think do you have any more questions for me today in this lecture? Everyone getting tired with SRC, I hope. I feel that.
Yeah, we have a couple of more minutes, so we can discuss some more if anybody has another question. We can also give some seconds to think about it.
Maybe just a very open-ended question. I've heard only a little bit about other effective theories that try to go a little bit further than the mean field model. Could you talk a little bit about some of the effective theories that we're currently toying with and trying to test?
For effective theory to test about the mean field model?
Yes, correct. That is, I feel like I've heard quite a bit about mean field models and the idea of a mean field is common in other contexts as well. But could you just tell us a little bit about any other effective theories that are currently being studied?
Let me see. Any other effective theory beyond that mean field, right? So for me, I thought mainly in the part of the GCF, I'm not aware much about other effective theory. So maybe there are the organizer of the school doing the theory here. So maybe you can comment about that in terms of theory calculation. You may have more information than me. Yeah. Carol? Yeah. I don't know if Carol's still with us. Yeah.
No, I am.
Yeah, so
I just got distracted with the sound of emails coming up here.
Yeah, I just wonder if from the theory side, you have more information about what other effective theories are ongoing for nuclear structure.
Of what? Sorry?
the effective theory to study nuclear structure beyond the mean field calculation from theory side. Yeah.
Like to study more nuclei, things like this.
Yeah, we are talking about it.
Yeah, it's because I'm not into nuclei, and no, I really don't know.
How about Alex? Do you have more information about it?
I mean, mean field theories are kind of old style, at least for like nuclei.
Yeah.
So they are still used in heavy nuclei, but you have to think that they are. I mean, if you remember the lecture of Artemis about the nuclear chart, mean field theory are made to fit some part of the nuclear chart. So you fit some parameters and you try to describe a sector of the nuclear chart. The idea now, at least in theory, is to describe everything from ab initio. That Dien show a lot of calculation that you saw in the talk are ab initio calculation. That means that you start from an effective Hamiltonian. Clearly, is effective because the underlying theory is QCD, and we cannot solve QCD so far, at least for nuclei. So you construct an Hamiltonian that is based on the most modern are based on chiral effective field theory. So the chiral symmetries, and you constrain the interaction between nuclei and nucleons using chiral symmetry. This has some advantage. For example, one that is very important for experimentalists is that you can somehow try to extrapolate an error. But then all the rest, when you have your theory, is to develop a calculation, I mean, a way to compute the nuclei, because solving the Schrödinger equation, even if it's not relativistic, is a terrible job, because it's a many-body problem that you have to solve. That's why Dien showed you the calculation for like nuclei that are ab initio. And also, if you check all the other nuclei that were computed, are practically the one that Artemis called the magic number nuclei. So it was oxygen 16, calcium 48, because there are calculation method that permit you to compute that. The idea is to use a single interaction to describe all the nuclear chart and all the phenomena. So from what Dien is talking today, that is short range correlation, so kind of high energy, to what Artemis was talking last lectures. So that is the idea of ab initio calculation. Clearly, I mean, it's kind of a big thing. It's like try to solve QCD at the level of low energy level. And clearly it's not so easy. So that's why still we need to describe experiment this effective model, this mean field models, in particular for nuclei that are kind of heavy, I mean, really heavy. My suggestion is that, I mean, low energy nuclear theories change a lot. It's not what was done 50 years ago. And it's kind of exciting. Sorry, this is kind of a commercial for what I'm doing, because I mean, you know that lattice QCD has tons of calculation, and maybe you like coding and so on, but also low energy nuclear physics. You solve a different equation. It's not anymore the QCD Lagrangian. You solve the Schrödinger equation, but the kind of effort and computational power that you have to put is the same, because the potential, the theory is the same. And that's all. I don't know if I answered your question. Really, if you just type on Google chiral effective field theory, you will find what are the most modern nuclear potential that are used. The other that Dien show is this argon B18. It showed a full list of potential that they were phenomenological potential based on meson exchange. So not only pion exchange, but also rho and omega and so on. They are kind of older, so they are not very used anymore, but they were very good in describing like nuclei, so they are still used for comparing the calculation right now.
Alex, is that another comment is that actually I didn't make the slide to show the result AV18 using in the contact formalism, but indeed that like data prefer the AV18. So it can describe the cross section of the different like for carbon 12, the reaction channel up to 1 GeV of the initial momentum. So we don't know what makes the AV18 like decrease so well compared to other one, but that look like preferable and then interaction to the real data. If you're interested in, we can talk about that more later. I didn't include that in the talk because I think it's quite a detail and we don't have enough time to cover that. Yeah.
Yeah, I can just add that this AV18 use meson exchange, so I'm not surprised that it describes well higher energy data. Chiral effective field theory has a cutoff around 500 MeV. So, and that's the maximum that it can go because it have at maximum pions inside usually. Nobody has so far, at least that I know, included meson exchange in the, I mean, use a bit of mass. So that's probably, and I'm sure that, I mean, chiral effective field theory is more controlled, but you can use in a range that is much lower in energy compared to AV18.
Yeah.
Right. Okay, so we ran a few minutes over time, but it was a very interesting discussion, a very active discussion. We should continue this. So let's take a break right now. Let's try to reconvene in 10 minutes at 10:15.